Okay, good afternoon, everyone. Welcome to EECS151 to 51A, Introduction to Digital Design and Integrated Circuits. Today, we're going to have our 7th lecture of the semester. We'll wrap up some of our discussion in combinational logic, and we'll start on finite state machine. So before we get into today's topic, another major news happened this week. I believe actually in our before lecture discussion this past Tuesday, Jason already mentioned Apple's new release of their A14 SoC. A couple of things very interesting this time. So typically Apple release their new generation of SoC actually associated with a new generation of iPhone. So you typically see a new SoC being released together with an iPhone, a new generation of iPhone. This year's release is actually really interesting. The first release of the A14 SoC, their newest generation of SoC, instead of actually together with a new iPhone release, it's actually together with a new iPad release. Although typically Apple's SoC, basically every new generation of SoC is actually being used in both iPhone and iPad, it is an interesting move this year where they only release the SoC but not releasing the new iPhone. So we'll see what their the follow-up announcement here. A couple interesting with this generation of SoC A14. The first thing, I guess some of you already noticed that Jason already mentioned that last lecture. Let me mute. So last lecture. So this is actually the first ever 5nm SoC actually being released. It is really interesting thinking about that. Actually, the most advanced generation of technology, right? We talk about Moore's law, the challenges associated with Moore's law. But as we're actually marching forward, getting smaller transistors, the latest generation of transistors is actually happening in the mobile space. We're looking at this, either mobile processors, either like iPhones or iPad. All those mobile processors is actually at the forefront of using the latest generation of technologies. So this is the first 5nm generation technology. Anyone remember what was the first processor was actually using the 7nm technology? Anyone remember? Well, it's also actually in the mobile space. The exact first, it is debatable, depends on whether you count the release date or announcement date. But both iPhone's SoC and also Huawei's Kirin SoC, those are actually the first processor, mobile SoC that are using 7nm technology. So this is really interesting, as I mentioned earlier, before we get used to actually waiting for Intel to release the latest generation, most advanced technology and see how that is actually being used in the server market. And now we are actually seeing a lot of the latest technology is actually being used in the mobile market first. One of the reasons, of course, the competition. There's a lot of competition in this market, and getting to the latest generation of technology definitely help in actually competing against other suppliers. At the same time, it's also because power and also energy constraints on the edge processor, you do want to use latest generation technology, and hopefully has a better power profile to help you with energy efficiency. So another interesting trend we are seeing these days is actually a lot of this most advanced generation technology is actually happening. We're seeing that in the mobile space first. Another thing interesting we're looking at, I also highlighted here. So this is actually the first Apple SoC, well, at least one of the first generations of Apple SoC that actually more than 10 billion transistors. So we mentioned when we talk about Moore's law, when we're thinking about transistors, we're talking about today's processor, even in the mobile processor, we're talking about billions or even tens of billions of transistors. So it's really exciting to see so many transistors actually being used and used to power this very advanced process and very complex functionalities. So this is actually, I guess, a cartoon-ish. This is not exactly diphoto, like being ready during the product announcement. The one on the right, this is a fairly cartoon-ish view. We'll see whether this actually matches with a diphoto exactly. But it is pretty interesting looking at how big the neural engine is. The neural engine actually takes almost like a quarter of the total die area. So considering that today's SoC, of course, we mentioned a lot of CPU and also graphic processing is also very important GPU component. We're definitely seeing more and more silicon area actually being dedicated to specialized hardware. And given actually neural network and deep learning in general is so useful and actually being applied in a lot of different applications, when we actually have more transistors, a pretty significant portion of the transistors are actually dedicated to specialized functions. So that's also very interesting. We'll see when we have more, like every generation of the Apple SoC, like after it's being released, you will see actually the diphoto being actually released or being actually reverse engineered. So it's also interesting to see how the exact area breakdown. But given we see a lot of transistors provided in this generation, in the 5nm generation technology, interestingly, at least in the official improvement, we are not seeing a very significant performance improvement of the overall, especially on the CPU front, but the accelerator, especially the neural engine, actually definitely get a very significant boost in terms of performance. So that's also a very interesting trend that's happening these days. Actually, first, I mentioned earlier, like these mobile processors, the mobile SoC vendors actually are one of the first in using very advanced generation of technology. Second, looking at today's modern SoC, we definitely see increasing amount of area is actually being dedicated using specialized specialized hardware. It's going to be really interesting given all of those. Like we talk about the fabless companies, all of those design companies, they actually all need to go to TSMC to fabricate their processors. And it's actually going to be harder to differentiate across all the different systems or hardware actually being fabricated from TSMC because they will all be use the same technology. There will be actually growing importance, especially for all those hardware companies, in how to actually differentiate themselves from other hardware vendors. And we mentioned like the NVIDIA acquisition of ARM last time. We'll see actually the importance of IP portfolio and how different hardware vendors actually trying to grow their design portfolio or their IP portfolio moving forward. Again, really exciting time, and we're seeing actually very interesting development these days, a lot of opportunities. And we'll keep everyone posted when we actually see interesting news. And it's also interesting, actually, we actually see more news. I keep updating this first slide because they're like different news, I think, worth mentioning. So we'll start with that, another exciting generation of SoC, and we'll see what happens next. So with that, let's get into today's lecture. So this past Tuesday, we started the discussion on the combinational logic. We talked about like the fundamental Boolean algebra and how we can use either sum of products or product sum, SOP or POS, to actually represent combinational logic. So in today's lecture, we're going to wrap up on combinational logic, mostly focus on how we can actually simplify the logic to reduce area and the cost of the hardware before we start on the finite state machine discussion. So for logic simplification, why does it matter? So we talk about how we can actually represent combinational logic, either using truth table or using Boolean equations, Boolean expressions, and then eventually all those different representations need to be actually mapped on hardware. We talk about early this semester, we talk about the important metrics in hardware design, and both cost and also performance and also in terms of area, energy, and also latency. All of those are actually very important metrics. So for logic simplification, the end goal is actually by simplifying the logic, we can get better design. It could be better in terms of area. We can minimize the number of units, the number of gates that we actually use in our hardware. It can also be better in terms of performance by reduce the number of either the amount of wiring in our circuit or the number of gates actually in our design to shorter the latency. And then as a result, we can have a higher frequency. So then the question is how what we can do to actually systematically to simplify all those logic to get better design. In today's lecture, we'll talk about some of the basically fundamental principles that you can do actually by hand to actually simplify the design. And those are also some fundamental principles that you see in today's synthesis tools that they use to simplify the logic design. Again, a lot of this kind of simplification is already taken care of by the tools, and the tools are actually very advanced. But as a user of the tool, it's also very important to understand what are the fundamental reasons and how the tools are approaching this problem. So with that, well, let's say what we can do in practically in making the hardware simpler by looking at the Boolean equations. So still, this discussion is still based on the Boolean algebra. We talk about different fundamental theorems or laws with the Boolean algebra. But in this topic, when we're thinking about logic, when we talk about logic simplification or Boolean simplification, a very important theorem that will be used is what we also call the uniting theorem. But basically, it's a combination of the distributed law and also the complement law that we saw last time. Basically, you will see an expression like this. It's like a sum of product expression. So you will have the x and y prime, and then being ORed together with x, y. What we can do is actually to take the x out, and then it become y prime or y. So based on the complement law, those basically y prime and y is basically 1. So in this way, you will see actually expression like this, we can simplify to be x directly. So this we can also see from the truth table. If we look at the truth table representation, we have two inputs, A and B. So instead of using X and Y, let's use A and B here. And the output is, we use F to represent output in combinational logic. So here you will look at the way we lay out the rows in truth table. Basically, every levels, we change one of the values in the first two columns, or first two rows and second two rows. So in the first two rows, only the value of B is changing, and in the like bottom two rows, only the value. Then in the bottom two rows, we switch we change the value of A, and also the value of B is actually changing here. So in this case, if we look at, you will want to use sum of product to represent F. Again, we're looking for ones in my truth table. And if we look for 1, those basically will be the highlighted region, right? So if we look at this expression, basically as long as A is 1, no matter what the values of B, it could be either 0 or 1, the output is always 1. So in this case, F is basically the same as A. And with this, basically one of the input is eliminated. We actually don't need to have any logic gates to represent this. We just basically directly wire A into the output. So that's an example of doing this, using this uniting theorem, to do actually Boolean simplification. This is actually very useful. You can actually keep applying this in more complex system or design. So I'm not going to go through this. This will be a very interesting exercise to go through this on your end. Like we talk about the full adder design and the carry out signal. And when we look at the carry out signal, basically the carry that we want to propagate to the next stage, right? So if you look at the truth table representation, here we list all the combination of A and B and also the carry in, and then R is a result and the CO is a carry out, right? And then we use the sum of product representation. We look at the output of my truth table when my carry out is actually 1. There are 4 rows here. My carry out is 1. And for each of the rows, we can write my mean term here. So let's go through one example. In this example, A and B are 1, and the C input, we look at carry out, A and B are 1, and C input is 0, right? So in this mean term, it should be A and B are 1, and then C input is 0. It should be this term here, right? And then we go through the bottom one, and the bottom row where C out is also 1, and A and B and C are all 1. So it will be this one. So we also mentioned earlier, we actually write the carry out directly earlier. It's basically 2 levels of OR gate here. And sometimes you also see people call this majority gate. Basically, looking at the majority of the signals, if the majority of signals are 1, the output is 1. If the majority signal is 0, the output is 0. So this is also a good example of the majority gate. So with that, like how do we actually convert from this expression, which is a unique representation using the product of sum of product format, and how do we actually turn this into this, which is actually more simplified version. We only have three term, and each term is two inputs instead of four term here, and each term is actually three input. Here, three term, each term is actually two inputs. So I will not go through this, but one thing is actually very important is actually what we talked about earlier, the uniting theorem. So in this example, you will look at this part, we're doing an A prime and then B and C, and then being OR together and being doing a plus with A and B and C, we can actually take B and C out, and then we're doing A prime or A, and then this will be 1. So we can actually eliminate one of the inputs in this expression. So keep doing that, go through this. After the class will be an interesting exercise, and then you will see actually how we get to the final expression, which is actually the same as a majority gate expression that we're using. So this is how we can use this uniting theorem to actually do logic simplification to simplify our design by looking at the Boolean equation. This is useful, it's also fun, it's also doable, but sometimes you actually may actually prefer more visual friendly way of doing this instead of actually keep handling each individual input or each individual term one by one. So an alternative way of actually also doing logic simplification, also using the uniting theorem, is what also people do kernel map or K-map method. Many of you should already see that in the discussion. We already have a preview of how you can use K-map to actually do logic simplification. We'll also introduce a little bit more into this lecture. So this is also an alternative way, instead of doing Boolean expression, which is basically, again, the same principle, just like whether it can be more intuitive in using a more graphical format. So this is basically still we're using the truth table, but instead of organizing the truth table as what we have seen before, basically each rows, it will be a unique combination of the inputs, and then the last column is the expected value of the output. So here we actually organize the truth table in 2 dimensions. And the reason we actually, or actually it could also be 3 dimensions, we'll talk about that in a minute. But we actually organize into these 2 dimensions so that we can see the adjacency more clearly. And the reason that we want to see the adjacency is that we want to explore the opportunities to using the uniting theorem to actually get rid of some of the terms that we don't need to simplify the logic. So for example, we actually have the 2 input. Instead of laying out my truth table as 4 rows in my truth table, we can actually lay out into like this kind of square where the different column here representing different value of A, and the different rows here and representing the different values, possible values of B, right? So since each value can be either true or false, we have 2 combinations. So here we have 4 entries, 4 cells in my kernel map. If we have 3 inputs, we can also do the same. Basically, we group A and B together. We have A and B here representing different column, and then C representing different row here. One thing you may notice here, as we listed here, we are using this gray code labeling. So gray code is basically another binary code where in every contiguous node code representation, only one of the values is actually 1 bit is actually changed. So you look at the combination of A and B, we start from 0, 0, and 0, 1, which is the same as the way we typically do binary coding. But instead of doing 1, 0, we're actually doing 1, 1 here. The reason is that we want to create the adjacency where only one of the input is actually changing so that we can see the uniting theorem clearly. So in this case, we actually, from 0 to 1, instead of doing 1, 0, we actually keep the 1 the same for B and only flip A. So we have 1, 0, 1, 1 here. And then in next column, we keep A the same and only flip B. So we have 1, 0. So here in every adjacent cell, only one of the input is actually different. So why this is useful? So with this adjacency actually being visually presented in this kind of 2-dimensional table format, it's actually much easier compared to using a truth table, the format that we have seen before, in finding the opportunity that we can actually group them together, basically applying the uniting theorem that we discussed earlier. So for this example, like we have two inputs. This is example we mentioned like how we lay out A and B earlier. So similar to the truth table, we actually, instead of writing the output in the last column, we actually filling each of the individual cell with the expected output for this particular input combination. So in this example, so if A is 0, B is 0, my output is 0. It's the same for A is 0, B is 1. But if A is 1, either B is 0 or B is 1, my output is 1. So after we're actually laying out the expected output in my kernel map, my next operation is trying to find opportunities that we can start eliminating, right? We're doing logic simplification. We want to eliminate terms here. So in this example, or in this case, we're basically trying to draw this kind of circles where between the adjacent cells, they are actually the same value, they are actually both are ones in this case. So we're looking for adjacent cell that we can draw circles, either 1 by 2 or 2 by 2, at least always need to be a power of 2. But we are basically drawing circles to actually find opportunities to eliminate unnecessary terms. So in this example, we have the two inputs, and I mentioned earlier. So if A is 1, no matter what the value of B is always 1. So in this case, by actually drawing circles, and we're basically saying in both two cells, the output is 1. And once we draw circles, we basically eliminate this B term because the value is actually independent of B. No matter whether the B is 0 or 1, my output is always 1, right? So in this case, by eliminating the B term, we basically say the output is the same as A here. For this which was originally a 2 input logic gate, but then eventually it's basically a single input wire in this case. And similarly, there are another case, we'll talk about the adjacency actually across row here. We could also find adjacency across column, which is this example here. In this case, as long as B is 0, no matter what the value of A is, either 0 or 1, my output is always 1. So in this case, it's actually a NOT gate, so B or inverter. So my output is basically B prime. We can also do this more. So if we have the 3 input, we can actually start drawing circles, and the circles can actually overlap because we always want to eliminate terms. It can be overlapped to maximize the opportunities that can start eliminating terms. So if we look at this, we have our AB layout in the horizontal across column here, and then C is actually specifying across row here. So this is basically the majority gate that we see earlier. So it's, and then we start drawing circles, and this cell is actually being shared in all the 3 circles. By looking at this, this vertical circle first, as long as A and B is 1, no matter what my value C is, it's always 1. So we have this AB term. And similarly, we can also draw a circle here and here to have my BC or AC term. So I mentioned it doesn't need to be always 1 by 2. We can also draw a bigger circle. As long as there are more opportunities, we can actually eliminate more terms. So here we start with a 3 input gate and eventually become only 1 single input is useful. So I went through this by words, but you can also follow this particular procedures to actually doing the kernel map logic simplification. You just like think about what we did before. So first we want to, given the number of input, we want to start drawing kernel map, right? So if it's 2 input, it's basically 2 dimension. If it's 3 input, we group one of the input, we group 2 of the inputs together, become one of the dimension, and another input to be the row dimension. So we first draw the kernel map with all the different input combinations. And then we fill in the map with the expected output from the truth table. Basically, we turn the last column of our truth table, which was where we are supposed to put our expected output into the individual cell of the kernel map here. And then we start actually drawing for groups of 1, we start drawing the circles, either 1 by 1 or either 1 by 2, 1 by 4, or 2 by 2, 2 by 4. It must be a power of 2 so that we can actually apply our uniting theorem to actually eliminate one of the input. Again, form as large as possible so that we can eliminate more terms, and also it can overlap, right? As long as it helps making larger groups, we can also overlap those groups. Right, and remember K-map is also periodical in all dimensions, and sometimes it's actually very hard you can also do cross if it actually has the two boundaries, because in the two boundaries, there are also only one element is actually different. So you can also draw across edges of the kernel map. So for each of the group, we are basically using this sum of products discussion, because we're actually drawing the group as ones. So basically for each of the group, we can actually draw a product term. And then by summing all the product term together, we can actually get a simplified function. So this is a very simple, like this is our truth table. So if we want to turn this truth table into kernel map, we split into the two inputs, different input dimensions, and filling my kernel map with expected output. Turn the last column of my truth table into kernel map, and then I start drawing circles. And whenever I have a circle here, it means at least one of the input can be eliminated. It doesn't really matter this. And for this is actually is basically an OR gate for this example. So a little bit, you probably already did some exercise in in the discussion. We'll have more exercise to help you to get more comfortable with this. But kernel map is actually very intuitive in providing this graphical format to provide opportunity to see what potential term can be eliminated. And a lot of time it's actually a lot more intuitive by instead of staring at the Boolean expressions, and using this can be actually very useful trying to figure out simplification opportunities. So in this example, we have just a quick example again. We have a 3 input gate and 1 output. So we split in this way. Here we actually do 2 columns and 4 rows. We group B and C together. And then we put the output of my kernel map, the last column, into the cells of my from the truth table into the cells of my kernel map. And then I start drawing circles, trying to maximizing the opportunities. So in this particular example, we can definitely draw a circle here, right? A 1x4 circle here because we have 4 ones in this case. And we can also see another circle here. It's a 2x2 circle. We also have 4 ones here, right? So by drawing a circle, let's do one circle at a time. So by looking at this circle, it basically first we can eliminate the A term, right? No matter whether the A is 0 or 1, it is always 1 here. And then another dimension we can eliminate is by comparing the 2 rows here, right? So B and the C. So in this case, we see no matter what the value C is, we can either 1 or 0, it's always 1, right? So this circle basically turns into B. So as long as B is 1, my output is always 1. We can do another exercise of this skinny circle here. So here we see actually the output, as long as A is 1, it is actually independent of the different combination of B and C. No matter whether it's B is 0 or C is 0, it's always 1. Right? So here in this square circle, we only need B. Basically, we can simplify all the way to B. And then in this skinny circle, we can simplify all the way to A. So for this gate, if we write our sum of product term, our product term eventually actually turn into A and B. So for this 1x4 group, it's actually A. For this 2x2 group, it's B. And we can also play with, like I mentioned earlier, we can also play with higher dimensions. So we can actually use a 3rd dimension here to introduce either 5 variables here or 6 variables in this case. We always want to, again, kernel map is all about the adjacency. So we want to create adjacency so that we can see the cells together where only one of the dimensions is actually different. So in the 5 variable case, we split to 3-dimensional table actually for a 3rd variable. And then for 6 variable case, we can actually stack them together. Again, we are still using the gray coding here because we all still want to create the adjacency. That's pretty much the max you can do is if you think about how you can visually see the adjacency using the 3-dimensional representation. So we typically, at most for kernel map, we go to 5 or 6 variables. So we talk about the sum of product term. I think Prashant last time mentioned earlier, like product of sum is basically the De Morgan. We can apply the De Morgan theorem. We can get the product of sum version. And similarly, we talk about how to use kernel map to do product of sum. Sum of product earlier by finding big groups of ones. And here we can also do product of sum. So the trick here is instead of finding ones, we actually want to find group of zeros. So that's also another way you can actually also see the equivalent, how those two expressions are actually equivalent with each other, and it really depends on which one has smaller number of terms. But for both, we can apply kernel map to simplify the logic. So a quick recap, we talk about the combinational circuit. Again, the outputs are only dependent on the current value of the input. So there is no state here. There's no memory in combinational logic, which is different from the sequential logic we're going to talk about in a minute, where we actually do want to have states to store or to remember where we are. And we have different representation to express on kernel map. We started with a truth table, and we talk about it's very useful. It's a unique representation, but it can also be tedious to actually write down all the combinations. And then we talk about how we can actually use Boolean algebra to actually express the Boolean functions or combinational functions. And then we can also using Boolean algebra theorems to actually simplify the logic. And alternatively, instead of using Boolean algebra theorem, again, the same fundamental, we can use kernel map, which is a more visual way to see the adjacency and apply the Boolean theorem directly. So again, I mentioned earlier in today's tools, CAD tools, they are actually pretty advanced, and then they're actually doing all those simplification directly. But it's still actually useful to go through this to understand the implications and also the opportunities in really in terms of different ways that you can express your logic. And again, this is actually very common questions that you will also be asked in job interview. So we also have some homework problems to help you to actually get comfortable with this. So that's basically what we wanted to talk about combinational logic. Specifically, we talk about the memory list feature, the Boolean algebra, and also logic simplification, how to use either Boolean expressions and also kernel map. So with that, we are also going to talk a little bit more about sequential logic and how we can build sequential logic, also express sequential logic efficiently. And a very important way of actually express sequential logic is actually the use of finite state machine. So we'll talk about the sequential logic building blocks, is specifically how we can build latches and flip-flops, auto transistor, not in today's lecture, but later. So again, you may notice our class is actually structured in terms of actually going through layer abstractions, and you will see actually more lower level design actually later in the semester. But we do want to actually get the structures constructed early on. So here we'll briefly talk about sequential logic, but with a special focus in thinking about finite state machine and how we can use finite state machine to express any sequential logic. And then we'll conclude this part in thinking about how we can express finite state machine in Verilog. So with that, let's get started. So again, we talk about combinational logic. It's basically memoryless, that we talk about the output is only dependent on the current input. So sequential logic, we mentioned also in the design implementation earlier, different from combinational logic. Sequential logic actually have state, right? We actually have memory. So the output is not only dependent on the current input, but also dependent on the current state of our design. So here, sometimes we also see people say it has memory because the output actually dependent on both the current values and also current state. And the current states are actually typically dependent on the previous value of the input. So the state is basically the information that we want to store about the circuit, and we briefly talk about latches and flip-flops and how they can actually be used to store state. We'll talk more about how we can use actually transistors to build latches and flip-flops later in this class. So specifically for sequential logic, we like to actually talk about how we can use what we call finite state machines to express the operations or computations in the sequential logic. Some of you may already see this discussion either in 61C or we talk about like combinational and sequential logic before. So we'll do a quick review here, but also focusing on how we can build different flavors of finite state machine. And this kind of notion of thinking about finite state machine is not only applied to digital logic, but also applied to like some of the software engineering principles in thinking about how you structure a complex software design. So the underlying principle is applicable in different disciplines. So again, it is a very useful representation when we think about sequential circuit. With all the sequential circuits we mentioned, the output is dependent by both the current inputs, but also the current states, and the current states are actually determined by the previous input. The reason we call that this is a sequential, this is a finite state machine. We talk about how we can use registers to store the state, and given n-bit registers to store the state, and then we can at most have 2 to the n number of different state combination, right? So you will have 10-bit to represent states. There at most can be 2 to the n. So that's why we call it finite, because there is a limited number of states. So by using the state-oriented way to describe a sequential logic, we can actually use the finite state machine to describe how the circuit or how my design is actually transitioning between the different states as a way to express the functionalities of my design. So it will be clear in a minute. We'll get to go through an example and also some of the associated building blocks of of finite state machine. So as I mentioned earlier, so finite state machine, we think about the sequential logic, right? Of course, we have input, we have external input, and we also have output, and the outputs are actually visible to the external world. It can be the final output, or it can be the input to the next stage of my design, right? So I have my input and output. The core difference between sequential logic and the combinational logic that we talked earlier is whether we actually have states, right? So instead, the output is directly dependent on the input in the context of combinational logic. In the sequential logic, when our output is actually dependent on both state and also my input combination. So with this 3 basically building blocks of any sequential logic, if you think about we want to use a finite state machine to express a sequential logic. So it will be always something like this. We need some state register, right? It's a finite state machine because we have the register to store the states. So we have some storage elements. We have our flip-flop here that can be used to store the states, right? And besides this combination, besides this flip-flop that we can use, we use to store the current states, there are typically 2 kinds of combinational logic actually also used in our design. The 2 kinds of combinational logic, the first combinational logic here, the one on the top, it takes the input and also a present state, and you go through this combinational logic to decide what my next state should be. Right, so if we have the limited number of states, and my circuit or my design basically need to go through all the different states or to perform certain functionalities, right? So to decide what my next state is based on either my current inputs and also where my current states are. So that's the first part of my finite state machine. It basically takes the current input and also current present state to decide what my next state is. Basically, this part of my combinational logic. Another part we talk about, we also have some external visible output, right? So to find what my output is, we also need to either take the state directly or take a combination of both the input and state. We'll actually talk about the 2 different flavors of finite state machine later, but basically we'll need another group of combinational logic that can actually be used to determine the output of my circuit. So for any, basically, whenever we talk about finite state machines, always have these three fundamental building blocks. The first one is the storage element, right? It has memory, it needs to store states. So we have this flip-flop that we can use to store states. And then we have these two combinational logic groups. The first combinational logic is used to tell us what my next state should be. And another combinational building block is actually used to tell us what my output should be. And then when we talk about states, finite state machine, the functionalities of finite state machine is basically described in what we call state transition diagram. We'll talk a little bit more what consists of state transition diagram in a minute, but at a very high level, we use basically the state transition diagram to describe the functionality of my sequential circuit or this particular finite state machine, so that we know how we can transition either between different states based on the input values, or how we can actually produce my output value, depends on where my current state is, and also sometimes where my current inputs are. So in today's class, we'll have actually a very simple example to express a high level what is a finite state machine and what are the different building blocks of the finite state machine, and why we actually need those two categories of combinational logic and also this flip-flop registers to actually store our current state. So in this example, let's assume that for some reason, we actually want to build a finite state machine to represent a cat's brain. So in this, we talk about for any finite state machine, it always have external visible input and also external visible output, and then it has internal state here. Right? So in this very simplified finite state machine example of a cat brain, let's assume that inputs to our cat brain are two kinds of input. Either it's the external user or external human beings are actually feeding the cat, is one of the input, and another input is actually petting the cat, that's another input. So for this cat finite state machine, it has two inputs, either it's being fed or it's actually being pet. And it has outputs, so two externally visible output. So in this example, we are monitoring the eyes and also the mouth of the cat to see whether the eyes are open or closed, or whether the mouths are also open or closed. So what are the states? So we talk about input. For any finite state machine, we have inputs and outputs, and then it also has some internal state to actually describe the current state of the circuit, right? So for this example, again, very simplified cat brain. Let's assume that our cat only has three very simple states. Either a cat is in the eating state, or in a sleeping state, or in a being annoyed state for some behavior based on our inputs. So again, the three components of finite state machine: inputs, outputs. We have the inputs are human behavior, either feeding or petting, and output is a state of our circuit. Here we're using the state of eyes and state of mouth to monitor the circuit, the cat brain. And internally, in our very simplified example, we have three states. So either in the eating state or the sleeping state, or whether our cat is being annoyed. So in this example, we talk about state transition diagram, right? So this transition diagram basically tells us how our circuit behaves actually with different input. So in particular, we talk about, again, the three components, right? The internal states of our circuit and the output and also input. So in this example, so the node of our state transition diagram is basically the states or the current state, the states of our circuit. So we mentioned earlier, we have, we have three states. Let's start with the eating state here. Let's say if the cat is in the eating state, and then for this current state, we actually specify the output that's associated with the current state. Let's say that if the cat is eating, the output of our cat FSM machine is actually, the cat's eyes will be open, so it's true. The cat's mouth is also open, so we also say it's true. So we use true, false to represent and to encode the signal here, encode the output here. And then, so we talk about, this is a state transition diagram, right? So basically tell us how the finite state machine is actually transitioning between different states. And the reason it is actually transitioning because it actually gets different inputs in our system, right? So in this case, let's say if while the cat is eating, we get another input, or get the feeding input, the cat will be still in the eating mode, right? So this edge of this arc basically go back to the node. It doesn't change the state. But if while the cat is eating, and then you start petting the cat, and then let's say our very nice cat actually will just transition into our sleeping mode, because actually he has enough, and then it will actually transition to the sleeping mode. So this is basically based on the external input, how my circuit will actually transition between different states. So in this state, we're transitioning from eating to sleeping state because externally we get this petting input. So if the cat is actually sleeping, how the output actually change based on the state. So in this example, the output, again, we're monitoring the eyes and also the mouth of the cat. So the eyes will be closed. We use false here, and the same with the mouth, because it doesn't, the cat is not eating anymore. So if we keep feeding, it doesn't actually break the circle. It will actually still in the sleeping mode. Cat is very sleepy. But while the cat is sleepy, you are still trying to pet the cat. That's when the cat is actually transitioning being annoyed mode. You're not supposed to touch me anymore. So here in the annoyed, in a different state, what are the externally visible output? Assume if the cat is being annoyed, or the cat opens their eyes, but the mouth is still closed. So if we keep patting, the cat will just still in the being annoyed state. And the only reason you can break this circle is try to provide a little bit more food to your cat so that we can go to the eating mode. Again, so this is a very simple example, but we want to use the example to think about how we can use different nodes to actually represent different states, and also by specifying the state transition diagram, it actually specifies the functionality, or how this FSM, how our circuit will actually behave with different input combination, right? So start from the state transition graph. Well, eventually we actually want to build a FSM in circuit to actually express this functionality, right? How can we actually turn this into our circuit to have a very simplified circuit representation of our cat brain? So after we have this state transition diagram, the next step is actually turning this into a table, basically turning this into a truth table. We talk about how we can actually use truth table to represent any circuit, right? So we also need to actually turn this into a truth table so that we can actually see how the input and output actually, how the input actually changing our state. So here in our truth table, or here we call this a symbolic state transition table. We'll see why we call it symbolic in a minute. But here we just use words to represent what are the states and how the states are actually transitioning based on different inputs. So here, again, in our very simplified cat example, we only have 3 states, right? So we have in our current state, we either in the eating mode or sleeping mode, or in the being annoyed mode. So we have 3 states, but we have 2 kinds of inputs, right? So either in the feeding, the cat is being fed, or the cat is being pet. So in this example, for each current state, we could have actually different inputs. So again, in this truth table, we list all the possible combinations based on the current state and also different input combination. It will actually could lead to different next state, right? So here we use this table to basically describe this state transitioning diagram, how our next state is determined by a combination of both my current state is what the current state of my circuit, and also what are the current inputs of my circuit. So I will not go through this, but as an example, like if we look at basically this edge here. So basically each edge associated with each input and then turn into a entry in our transition table. So if the cat is in the eating mode and we keep feeding, the next state is still eating, right? So we're still in the eating mode. But let's go one more example. But if the cat is actually in the eating mode and you start petting your cat, very likely the cat will actually, well, in this case, it's actually deterministically, the cat will actually go into the sleeping mode. So here, by actually encoding all the combination of my current state and input, and then we know what the next state is. right? So it is symbolic because we eventually want to actually express this in circuit. And in our circuit, we need some way to represent all the different either states or the different inputs. So the next step of our FSM design is actually to turn that symbolic state transition table into this encoded state transition table. So what do I mean by that? So for each, we actually need to explicitly encode our state and also our input, how we would like to use different values to represent our states and also our input. So here, for this particular encoding, let's just say we do this very simple binary encoding. We talk about we have 3 states, right? So for 3 states, we need 2-bit to represent different states, right? So we start with eating state, 0, 0, sleeping state is 0, 1, and if it's being annoyed, it will be 1, 0. So this is our state encoding. So here we basically translate our symbolic state transition table here, where we're actually using words to describe the status of the circuit into this encoded, right? So the eating mode will be 0 and 0. So we have S0 is 0 and S1 is 0. And you see in the sleeping mode, it should be 0, 1. Yeah, actually this is correct. So the zeros, and so we do is 1, and then the zeroth bit is 1, and the first bit is 0 here. So 0, 1 is the sleeping mode, and being annoyed is 1, 0. And so this is a state encoding here, right? So those first 2 columns are representing how we actually like to encode our state. We also need to encode our input. Let's use X to represent our input here. So here we only have 2 inputs, right? So either feeding or padding. So here we basically have a binary encoding for our input. So if it's actually feeding, we say the input is 0, but if it's actually padding, the input is 1. So it's either 0 or 1. And then next state, we can basically, it's again using the same state encoding, right? So here we basically turn this symbolic state transition table into our encoded state transition table using this particular encoding format for both my states here and also my input, my binary encoding of my input X here. And then this looks very familiar to you. This is basically our choose table, right? We talk about how we can use the choose table. We can turn the choose table into a Boolean expression using either sum of product or product of sum, right? Let's just quickly do a sum of product representation here. Let's do S0, which is the next state, right? We want to see how my next state, the first bit or the 0th bit of my next state is actually determined by either my current states and my input. So we're doing sum of products. So we're looking for ones of my choose table. So we see 2 ones here, right? So the second row and the third row. So then we're using our min term to actually express this into my sum of product term. Oh, here, this need to be broken actually. This actually should be separate bar. So it's S1 bar and S0 bar instead of shared bar. Here, it actually means different thing here. So by using the min term, so this will be S1 bar and then S0 bar X, and that will be this term. And then this part will be S1 bar here, and then S0, and then X bar here, right? And then we can actually apply the Boolean simplification that we mentioned earlier. Let's see whether I can actually break this. Let me break this explicitly. Okay. So by looking at this Boolean we can actually simplify this. So it will basically be X0, XOR X, and then end with S1 bar. We can do the same thing for S1 prime or S1 bar. We will not go through that in this example. But again, we turn this state transition diagram into something we're very familiar, right? We talked about this already, choose table to Boolean expression already in the combinational logic. So after we encode our states and input, we can turn this, turn the state transition diagram here. And by doing this, we actually know how my outputs actually will be determined by a combination of how my next states. So here, the next states, we're using S to represent states, right? How my next states can be determined by a combination of my current state and my input. So we talk about 3 very important components of any finite state machine: the inputs, the outputs, and the states. right? So here we know actually how our states transition, how the next state is actually determined by a combination of current state and the current input. But then the next question is, how about the output, right? That's also another, how do we know what's the output of our circuit? So again, to actually express that, we basically list the truth table of our output here. So if we look at the output in this example, right, our output, basically the eyes and the mouse movement of my cat is actually only associated with the state. Here it's not associated with the input. We'll talk about why it actually matters in a minute. But in this example, we can actually use the same encoding or state encoding to represent the current state. And then we can also express our output. Again, we have an encoding for our output. Here we're basically doing a version of one-hot, well, not one-hot encoding. We basically, we give a 1 bit for each output, either eyes or mouse. And if they're both open, we say both are 1. If they're both closed, we're 0 and 0. But if one is open, the other is closed, it's 1, 0 here. So we encode both the state. We use the same state encoding as what we saw before. And then we encode the output of our eyes movement and also the mouse movement. Again, once we see the truth table, right, we can also turn that into a Boolean expression here. Let's just do one of them. If we look at the M output here, so M, the cat's mouth is only open if actually it's in the 0 state, when both S0 and S1 is 0. And this 0 state represents the eating state, right? So here to encode the M here, basically it's S1 bar and with S0 bar. And here, I believe this is also to be. So it's S1 bar and S0 bar here. Okay, so here before we talk about how we can actually encode our states and express the next states using from this state transition truth table. And here we talk about how we can actually express our output and then get this Boolean expression from our output truth table. Right, so we talk about the 3 representations of combinational logic. If you still remember, like with our truth table, and then we can use Boolean expressions. And then the 3rd representation is basically the gate level representation, right? How this can be turned into circuit. So once we actually have our output, how we can express our output, and also how we can express our next state, we can actually build this cat brain, this finite state machine of the cat brain, in hardware, in gate level representation using fundamental logic gates here. So if you recall at the very beginning, we mentioned for any FSM, 3 very important parts. We have the state register, we have flip-flop to actually store the states. And then we have 2 combinational logic. One combinational logic is used to actually compute the next state. And another combinational logic is used to actually compute the output. Right, so that's 3-part storage element registers, and also 2 combinational logic to compute the next state and the output state. So here we start from here. So this is our Boolean expression of the next state. We use S0 prime and S1 prime to represent the next state, and also the output. How we actually have different output based on the different input. So if we look at our gate level representation or a potential way of circuit to execute to represent this finite state machine, right? The first thing we see is this flip-flop. It should be actually 2 flip-flops here to store the states of our circuit, S0 and also S1. And then we'll have 2 combinational logic. One is actually to use to represent the output based on the circuit, based on our current state. So that's basically this part of my design, right? So based on the current state, S0 and S1, we will actually have different output, the visible, externally visible output of my cat, FSM. So it's either whether the cat's mouth is open or closed, or whether the eyes of the cat is actually open and closed. And here, it's basically an inverter for the for the eyes movement. And also we have, well, basically inverted S0 and S1, and then with an AND gate to the mouse. And this, if we apply De Morgan's law, if we do the bubble pushing, this can be turned into a a NOR gate, right? So this part of the circuit basically represent how we get the combination logic that we use to get the output. And then the left part of the circuit is basically how we can actually calculate the next state, right? Given my current state and my current input, we will have actually, we'll go to actually different next states, depends on the combination here. And as what we just calculated earlier, the Boolean expression of our next state transition, and then we can also turn that into this gate level representation here. So this is basically an example of how we can actually express or we can build a finite state machine, start with the state transition diagram, understand how the state, how my circuit actually behaves with different state transitions, and then get to the, what we call symbolic state transition table, using words to actually express how the states actually transition between different states. And then we can turn that by providing a specific state encoding and also input and output encoding. We can turn that into two truth tables. One is a truth table to express a state transition, how I get to next state based on our current state, and another truth table to represent how my output is actually determined by either my current state or a combination of my current state and my input. And then we can do what we already seen before, right? A logic simplification, either using kernel map or just purely looking at the Boolean expression, and then getting a simplified logic, we can turn that into a gate level representation, and that will be our hardware, our sequential logic, sequential hardware to describe this finite state machine. So this is what the finite state machine is. We'll talk a little bit more before talking about like different flavors of building finite state machines and how we can actually turn that into hardware. Before we move on, I see, oh, there we have a couple of questions. So Mitchell is asking, what values would the flip-flop of S1 and 0 be initialized to? So that's a very good question. That's a very important question. So in this simplified example, we actually haven't, we actually don't have an initial state or a reset signal. So typically, almost all required, you actually always have a reset signal and also initial state. Basically tell your circuit or describe your circuit into what the initial state is, what are the initial values should be for your circuit. In this example, there should be actually an initial state and take reset signal as another input instead of just the external input. With the reset signal, we actually specify what's the initial values of my circuit. So in this very simplified example, it doesn't have, but in the real example, you always need to have a reset signal and tell your circuit what's the initial behavior of the hardware. Very good question, Mitchell. Okay, so before we move on, some logistics of the class. You get to see more in your lab 3. Hope you all enjoy lab 3. I think most of you have already checked off lab 2, but if you haven't, time to wrap up. And we do have a couple of students who just joined. Again, welcome, but time to actually catch up. Make sure you, especially on the lab part, don't fall behind. And we're actually starting a new lab. You should already see a new ASIC lab yesterday, and we're starting a new FPGA lab this week. So every week we're introducing new components. Don't fall behind, and use lab as a very important opportunity to actually see how the different concepts we talk about in lectures can be used when you're actually building hardware. Again, homework 2. Like Ivy mentioned, homework 2 is helpful. So homework 2 is due tomorrow. Make sure you finish that, and we'll have a new homework will be out either tonight or tomorrow. A little bit more about midterm 1. The teaching staff is preparing the first midterm. It will be in class, so it will be our Tuesday class slot. It will be October 6th. We will prepare a review session before the midterm so that you can review important topics and also asking our teaching staff for questions. This is a link to the exam policy. All of you should already have reviewed the exam policy. Take a look at it and let us know if you have any questions. As a first step to get you started, it's time to actually create your Zoom meeting ID that will be used for the midterm. So again, look at the exam policy to see the instructions. and submit your Zoom meeting ID to the teaching staff via this link. So all of you should actually provide us a Zoom meeting link so that we can actually join your Zoom meeting during the exam. I think that's all the important questions. Again, if you have any questions with homework or labs, and also with exam, feel free to reach out to us. We'll either PSL or individually, but we're happy to clarify anything that you may think helpful. Okay, so with that, let's just quickly review. We already mentioned that the FSM design process. We need to actually start with specify the function of our circuit, sequential circuit, what this FSM is trying to do, and then draw the state transition diagram, list all your state and how the states actually, how your circuit actually transitions through different states based on different input combination. And then as the first step, write down the symbolic state transition table. That's actually very helpful to think about how the state transition, how you convert from this diagram format into a table format. And then to make it actually a real truth table, you need to really think about what kind of encoding you like to give for either your states and also your input and output. So most of the time we are actually using binary encoding here. So that's basically the example that we went through is we have, let's say we have 4 states. We need 2-bit to represent those 4 states, either 0, 0, 0, 1, 1, 0, and 1, 1. Right, so this is basically the minimum number of bits that you need to actually represent these states. Sometimes you may actually find useful to use different encoding format. For example, sometimes maybe using one-hot encoding, which is also a very popular way of actually to encode the behavior of the circuit. It's basically using 1 state per bit for each of the state. So let's say in the same example, you have 4 states, right? So instead of actually using the 2-bit combination here, we actually use 4-bit. But here, only 1 state bit is true actually at any given time. So if it is in the first state, it will be the first bit is 1. In the second state, the second bit is 1. Third state, third bit is 1. Fourth state, fourth bit. So that's why it's actually 1 hop, right? So 1 hop. So basically only 1 bit is hot actually anytime. You may already notice you actually need more flip-flops to actually store that. So instead of 2 flip-flops, you actually need 4 flip-flops to store it. But depends on, you may actually see different encoding when we have this encoded state transition table, will actually give you different Boolean expression to express the transition. And sometimes actually, even this is a little bit more expensive with more flip-flop, you could actually lead to a simpler circuit to represent how the state transitions between input states and between current states and next state. So encoding matters, and this part from symbolic to encoded is always dependent the particular encoding you have. And then the following part should be actually very straightforward, right? We already talked about that in the combinational logic. So you get a truth table, you can actually get your logic expression, Boolean expression, and then you can actually draw the circuit. One thing different is that instead of just a combinational circuit, you have actually need to have flip-flops to store your states. So that's a very general design process. Again, you'll actually see more in both either your labs and also homework. So we'll have more exercises to help you to get familiar with us. So we talk about the introduction and use this example, thinking about how to use FSM to actually describe sequential circuit, and also Mitchell represent a very mention a very important thing. Actually, you need to have an initial state and reset. So next, we're actually going to talk about 2 different flavors of building finite state machine. The Moore and Mini. Both are actually very popular. And we probably don't have time this time, but in next time, we'll actually see how we can build FSM in Verilog. So when we think about finite state machine, if you remember what we had before in the simple CAD example, right? So inside each of the circle, inside each of the node, we also write down what the output should be, right? And if you think about what we had before, the 3 components of a finite state machine, we have the state register to store the states, and we have a combinational logic to combinational logic to decide what the next state should be, and another combinational logic to decide what what my current output should be. So here, the differences between the Moore and Mealy finite state machine is actually focused on the second part, the second combinational logic that we mentioned earlier, the combinational logic that we use to determine the next states. So, to determine the output. So what are the two different flavors here? So here are the example of, let's start with Moore finite state machine. Okay, both are actually named after like two researchers in this area. This is actually different from Gordon Moore. We actually see Moore a lot, but this is actually a different Moore. So again, as we mentioned earlier, in any finite state machine, we have the state register here, and we have the next logic state to determine combinational logic to determine the next states, and we have another combinational logic to determine the output. So there are two flavors in thinking about combinational logic here. In both cases, the next state is always determined by your current states and also your input, right? So the next state is also determined by both your input and your current state, right? You need to see the input to decide where you go. But there could be actually different flavors or different principles when you think about the transition of your output. So one school of thought in thinking about output logic is to make it actually only dependent on the current state. So the output, we see actually there's no edge from input to output. So output is actually only dependent on the current state. So this is what we call by Moore FSM. So for given each current state, we actually know what my output is. But an alternative way of thinking about deciding the output, this part of the combinational logic, is to what if my output is not only dependent on my current state, but also dependent on my current input. So in this example, both my next state and also my output state are dependent both of my inputs and my current states. So those are actually basically two different flavors of thinking about FSM. Again, the only difference they have is to think about the output logic, whether it's only depends on the current state or it actually depends on the combination of current state and the current input. So why does this matter? What are the different implications of the two different choices in thinking about a finite state machine? Let's use a very simple example here. So again, whenever we think about finite state machine, the three parts, right? The input of my circuit, and also the output of my circuit that is actually visible externally, and the inside, the state register that we use to store the states. So here for the input, we are building an edge detector. So in this case, when we think about edge detector, we're basically having an input bit stream. It's a digital input, so either 0 or 1. And it is an edge detector or pattern detector in the sense that we're basically looking for a particular pattern. And we're basically looking for a pattern that we see a 0 to 1 transition. That's why we call it an edge. So here, the output is either 0 or 1, right? So it's a 1 bit. Basically, in our edge detector, we set our output to be true or to be 1 when we actually observe this pattern of 0 to 1 transition, which basically, as we mentioned earlier, like this is a rising edge, right? So whenever we see a rising edge, we actually set our output to be 1. So how do we actually build a finite state machine for this? As we mentioned earlier, we start with a state transition diagram here, right? So in this example, we have 3 states here. So the first state is 0 state, and the next state is actually the change. We'll talk about what we mean by the change state in a minute. And the next state is what we call the 1 state. So 0 state is basically we haven't seen anything. We just see 0 in our state. So this is what we start with 0. And here, whenever we set our state, we also set or specify our output. So when in the 0 state, we either only see 0, we haven't seen a 1 yet, so our output shouldn't be 1, right? Because we only set our output when we see a transition. The same as our 1 state, when our input is actually 1, that's also not the behavior we're looking for. We only set our output in this change state. This change state is basically where we see a 0 and it's being transitioned to be a 1. So the output is actually only associated with our change state. So let's go through this state transition diagram a little bit more. So let's say we start from the 0 state. This is where we start. If my input is also a 0, so I already see a 0. If my input is another 0, I don't change my state because that's not the pattern I'm looking for, right? So if I'm already in the 0 state and I'm seeing another 0, I stay in my 0 state. But if I'm in the 0 state, but I see a 1, right? So this is a 0 to 1 transition. Once I observe a 1, I get to my change state. And in this state is actually where I set my output to be 1. So if I'm in the 0 state, I see a 1, and this 1 triggers a transition so that we actually get to the change state. So the change state, I set my output to be 1. And in the change state, so this where I already see a 0 to 1 transition, right? So I can either, then I need to take another input, right? It can be another input, either 0 or 1. One thing you notice that in the change state, we don't have this self edge, right? So if I see, after I see this change, and then if I see a 0, right? This is not the pattern I'm looking for, right? This becoming, I see a 1 and then I see a 0. This is a 1, 0. So it's actually a falling edge. So this is not the pattern I'm looking for and become a 0, so I go back to my 0 state. But if I'm already seeing a 0 and 1 and I see another 1, so I go to the 1 state, signaling I already see a 1 instead of 0. So then I transition to a 1 state. You may notice that this is actually the only state where I don't have a self edge, because after my change state, I'm not observing this 0 to 1 anymore. So I either go back to my 0 state or I go to the 1 state. And similarly, once I'm actually in the 1 state, meaning I'm seeing a 1, again, my output should be 0 because this is, again, not the edge I'm looking for. And then I'm seeing another 1, I stay in the 1 state. But if I'm seeing another 0, I transition back to my 0 state. So that's basically the different input and the 0 and the state. We specify the 3 states, and then how we actually transition based on the different input pattern to the next state, and also the output. So this is actually a combined state transition diagram table and also the output table. And here you may notice our output is only dependent on our input. So once on our current state, right? So if I'm in the change state, my output is 1, but if I'm in either the 0 state or the 1 state, my output is always 0. So this is actually an example of the Moore machine that we discussed before, because the output, we actually write the output as part of the node in our state transition diagram, because my output is actually only dependent on the current state. So in this example, we can actually turn this, remember after we get to the state transition table, we can actually it becomes a combinational logic problem again. We have a truth table, we can turn that. We can use, like in this example, we can actually either using Boolean expression or use kernel map to actually simplify the logic. So here we can actually specify the encoding and see how my output, both my output and next state is actually determined by a combination. For next state, it's determined by a combination of input and current state. And for the output, it only depends on the current states. So I will not go through the kernel map example in this during the lecture, but feel free to go through that and see how we can actually simplify that. And then once we have this Boolean expression, we can turn this into actually a gate level representation. So this will be what's the circuit for our finite state machine. And in this example, you see our output is only dependent on the current state, while the next state is actually depends on a combination of my current input and my current output. So this is basically our Moore machine. You may notice that we have 3 states here, and we use 2-bit to represent those 3 states, and my output is only dependent on the current state here. So that's one way of building a finite state machine. And we mentioned that there is an alternative way, what we call the Moore finite state machine. Let's go through this quickly, but we'll also talk a little bit more actually in the next lecture, so don't worry about that. So at a very high level, if you look at the state transition diagram, you may notice that instead of putting the output in the node of our state transition diagram, we're actually taking the output out as part of the edges of my state transition diagram. So my node only represents the states, but my output actually depends on the different input of my design. I may actually have different output. Let's just do one of them really quickly. So if we start from the 0 states, we'll see actually if my input is 0, and then my next state is still the 0 state. So this state transition is the same, but my output is also 0 in this case. But if we actually have a 1 input here, my output, because I have actually, because this is basically 0 to 1 transition, as long as I see as this 0 to 1 transition, my output is actually set to 1 immediately at the same time I transition to my next state. So this is just a quick example. You may wonder, why do we want to do that? What are the differences? Don't worry, we'll cover that in the next lecture. So we'll talk about the differences more and mealy, what are the benefits of using mealy machine and what are the differences. And then we'll conclude this part by how we can use Verilog to discuss, to write finite state machine. Again, it's good to see you all here. And if you have any problem or questions, feel free to reach out to the teaching staff. Have a good week and enjoy the lab, and we'll pick it up here in the next lecture. Okay, good to see you all. Take care.